without further ado, I'm going to pass it to Aditya to talk about the denoising autoencoders. Let's give him a round of applause.
All right, thank you, Max. Okay, yeah, we can just start with the next slide. The idea of the project is to build a autoencoder model or a neural network, which would essentially remove the noise from your imagery. That could be static noise, it could be a few random pixels here and there, and then essentially give you a clean image altogether. So just a brief recap on what exactly autoencoders are. Well, essentially it's a model which takes your input data, reduces its dimensionality while keeping only the most essential features of that data, and then reproduces it back to the original size in a target form that you want, or even the original for some applications. But yeah, that's what an autoencoder essentially is, and that's what we're focusing on building. Could you go to the next slide, please? Right. So I'm just going to go over the progress that we made since this is the mid-semester progress presentation. Most of my members, okay, who over here was in my team? Could you guys just raise your hands for a sec? Yeah, so as of now we have Yusuf, Tanisha, and, excuse me, could you remind me? Tao, right, I'm so sorry. So we have these three, and then we had over, that means we had another 10 people who joined us initially. A total of 4 people had dropped out now, so we have 10 people remaining in the project, and we're going with 3 sub-teams of those. So in the first week, since most of us were unfamiliar with the topics, I created a few beginner-friendly notes, a few information documents, I curated a few resources for them, and we made sure that everyone has a proper foundational understanding. We spent the first week purely on studying all of the necessary topics. So that's like neural networks, working with PyTorch, activation function, the different kinds of layers, etc. And the idea, like I mentioned in the bottom of the slide, is a solid foundation for the rest of the development cycle. Next slide, please. So, week 2, you have the theory. We wanted to have a very small demo so that our members could actually understand the end-to-end flow of it. So I made a quick little notebook based on an article I found online, but it did have some errors, so I fixed it, and I gave them working code in the Jupyter notebook with an end-to-end functioning autoencoder for the MNIST dataset. So that's like the dataset of digits from 0 to 9. We added some Gaussian noise within that dataset in the data loader itself, and then we taught the model to kind of remove that noise, and it was functioning pretty well. I like to think that the members had an idea of what to do because they performed remarkably well afterwards in the subsequent cycles. So yeah, next slide. Third, so now that we have an idea of the end-to-end cycle, we have the concepts, we begin working with the actual dataset we wanted to work on. So the natural images with synthetic noise dataset was one that we found that was a medium size and workable. It had 512 by 512 3-band RGB images. So we obviously had to redesign our autoencoder to accommodate these 512 by 512 images with proper dimension reduction and making sure the matrix dimensions were working properly. And we tackled the denoising task. We got the training up, it was working fine, except, could you go to the next slide? This happened. So evidently we made a big mistake somewhere, because after the first and second epoch, the learning kind of, well, you can say it plateaued. And this isn't a very good loss metric, by the way. 0.33 is a really, really bad number that we have. And even the PSNR of 5, so that's measured in decibels. The idea is to get to around 30 decibels, 30 to 50 for a good image. If we're sitting at 5 and plateauing, something definitely went wrong. So we explored the architecture, we looked at exactly what went wrong. The issue was there was a sharp dimension jump between the last convolutional layer that we had and the latent dimension layer that we had. So we obviously corrected that. And next, architecture changes. So apart from the dimension change, we changed our activation functions from ReLU to SILU because a little bit of research I did showed us that SILU having a smoother change at 0 would kind of accommodate the model learning better. We went for group normalization instead of batch normalization because turns out with batch normalization and small batches, you end up retaining a lot of noise within that particular layer and that hinders your learning. But group normalization is a lot more friendly with smaller batches, and because of computational limitations, we stuck to that. Next, the fully convolutional latent space. So, when we had 512 channels at the last convolutional layer, each with an 8 by 8 filter, you end up with a few 32,768 individual parameters. So when we accommodate that into the hidden layer, it generates a huge number of parameters, which severely bottlenecked the compute, and it also made a mistake with how it was retaining our features. So we swapped that out for a fully convolutional latent space, so we saved up on parameters, and we retained spatial information. And yeah, we removed the dense bottleneck. Apart from this, we also modified the learning rates. So instead of a 1e negative 3, we went for a 3e negative 4 because a few articles and a couple of research papers cited that to be more effective with our optimizer. And we changed our loss from mean squared error to L1, which was a little more preferent towards edges, edge-related features, but you will see where that came into play with our demo. Next. There, so this looks a lot better, right? After all those changes, we ran it, and by the way, even the previous one had early stopping in it, but because it was infinitesimally reducing in loss, it just went down for 35 epochs. This one trained for the full 100, and you can see it was still reducing. So possibly we could have kept it going on for longer, but because early stopping was on the validation curve, it stopped here with, at our best loss, about 15 epochs prior. So over here, we reached almost 22, 23 decibels for the training set. And we went over 20 for our test set, which I'm pretty happy with for our second iteration. And it's only up from here. We're currently, next slide. Right, so this is some inference. The projector is not doing it its due justice, but I will still go over it. So the couch happened to be one of the better images that we had because there are no smaller, finer features within the couch itself. It is removing the noise, it's understanding the color well, and it's really good with edges. You'll see that as a commonality across all 4 images, but it is really bad at retaining finer features, so we're working on research right now to be able to retain those finer features. In the other landscape image as well, in the top right, you can see that the overall picture is retained really nicely, and because of the lack of detail, it does look nice as well. But the bottom 2 images kind of clarify why that's a problem. Here, there are actually trees with leaves. Thank you so much, Max. We're back to square one. That's fine. So the trees over here are actual leaves that were visible, but here they're just black blots. And in the bottom right image over there are trees in front of the building. You can barely see them, unfortunately, but yeah. And in the denoised image, the trees are gone because the model just did not want to learn those finer features. So we obviously do need to make a few changes, but I'm quite happy with the progress we've made, given that we started off with just studying all the topics and actually getting through this. Next. Right. So this is where we are right now, week 6. I've shared a few research papers with our members, and we're also looking at others, and we're currently studying those papers with existing state-of-the-art architectures. We're probably going to be incorporating a few UNet-style skip-connect connections. We're going to be working on cyclic learning rates, maybe, to see if there's any local minimas that the model is getting stuck in on the loss curve. And we're going to try a few hybrid loss functions. So now, since we used L1 last time, I did do a little bit of search and found that SSIM is apparently the existing best function for vision tasks with autoencoders. So we are going to try a hybrid loss function to see where we can go from there. And essentially the idea here is to work towards a finer detail preservation, which was a weak point in the previous iteration. And next slide. So yeah, overall, we have a solid conceptual foundation when we started off from almost nothing. We have established a baseline with the CIFAR10 dataset, sorry, not MNIST, CIFAR10. We went through with our initial dataset run, it failed, that's okay. We modified that architecture, we improved from that. We got a decent functioning model now, and now we only look at improvements. The next phase, like I mentioned before, implement model changes, hybrid loss functions, and just keep experimenting, try a few new hyperparameters here and there. We're a pretty big team, so I think we can get it done. And yeah, that's just about it from me. If you guys have any questions, then go ahead. Otherwise, thank you. Go ahead.
After your team, I don't want to say failed, but the first thing that you did, it didn't really work.
You can say failed.
How did you manage this failure in terms of, people get upset, they think that nothing is going to come out of this, and a lot of people drop out, I assume. So how did you make sure that the team morale is up and that you can just keep going towards the goal that you have?
So conveniently, I was very lucky to have fairly resilient members. The dropouts actually happened before those results came out, the little bit that happened. And everyone was open to the idea that, okay, we won't get it perfectly the first time, but we can improve it. Thankfully, everyone was on board with that same mindset. So I took responsibility of checking out the architecture because I had more experience within my sub-team. And yeah, after that, we had the insights. We made the required modifications. We established the training run. I shared those changes with them. I told them what happens and why it is done the way it is. And yeah, after that, we ran the second training run and it worked out.
Thank you.
Go ahead.
Do you have the original images with no noise
Yeah.
in your data set?
Yes.
How do you measure PSNR between generated images and the actual one?
Yes. The loss is also measured between the output of the model and the reconstruction loss is the output of the model versus the ground truth image without noise. Obviously, we want to reconstruct it in a denoised manner, so that's what we're measuring our loss against. Okay? Yeah, go ahead.
How did you make sure? So it sounds like your project was more on the entry level, right?
Yep.
And how did you ensure that people who are very entry level, they still stay on track? It doesn't feel like they're overwhelmed with all these new concepts as a project leader.
So, A, I kind of took it the way I would have liked it to be presented to me during my undergrad. B, I revealed those resources as well in a staggered manner. And when I gave them the bunch of resources in the beginning, I also gave them a starting point and sort of a quick start on a few smaller ones that they can get done with first. And they can explore the others in the resources if they want deeper technical understanding. And I also curated some of the documents myself. So I made sure that those were going to be as simple and as layman as possible. Plus, we also used to have weekly meetings for a while where we would clarify doubts. So I made sure that everyone was clear as much as I could. And whenever they do have doubts, I do discuss with them as required. Yeah.
And for the next semester, say you run the project again,
Mm-hmm.
what would you have done differently compared to this semester?
As of now, until I have my results, I wouldn't be able to reflect perfectly. But within this particular phase, I would say I should have probably looked more into the consequences of the kind of architecture I was building for the first 512 by 512 iteration. Because in hindsight, there were a few glaringly obvious problems that I should have noticed. For one, in the architecture, the output was passing through a sigmoid function, which would limit the range of the output between 0 to 1. But our data loader, silly enough, was normalizing it between -1 to 1. So even if our ground truth images were between -1 to 1, and our model output was 0 to 1, that would objectively result in a huge amount of loss, and the model would not know what to do, because it's a data loader issue. But I made that mistake. So there were small things like that you just kind of had to pay more attention to. Go ahead.
How long did your model take to train?
The first one, it was rather slow because most of my VRAM was used up, but it took, I think, an hour and a half. The second model was a lot faster because the purely convolutional bottleneck, and that was done in like 45 minutes to an hour max. I literally put it to run. I went to make dinner. By the time I was done eating dinner, the model was trained, and then afterwards I just ran my inference. Yeah, Krishna.
Yeah. So how do you know everything is working? Is it just a human in the loop approach, like you see, okay, the image is now denoised, or is it in the matrices you see, okay, according to this matrices, it's even more better?
Do you mean metrics by any chance? Like the PSN? Yeah, so we did have the graphs for the PSNR values, right? Earlier on. So we were obviously looking at those along with our loss graphs to make sure that everything was on track. We didn't want to, obviously, yes, human inspection is a good way to start, but there are going to be pixel level problems that human eyes can't see. So that's why we keep track of metrics, because that's important.
Good, did you?
Thank you so much.
That's pretty cool. How many?